Thanks for the intro. I'm really excited to be here. My name's Jesse. I'm going to talk today about robotic surfaces. This is work I've done as a researcher at Carnegie Mellon. You're looking at an example of a robotic surface right now. This is a physical surface that you can control. Here we're using this grid of bubbles to kind of steer around this metal ball. And now when we talk about robotic surfaces, or at least when I do, we're usually talking about surfaces that are composed of a bunch of different cells. And when we program a surface, what I mean is that we're able to use software or some kind of information to manipulate the physical status of these individual cells. So this is useful for things like dynamic textures. We've been able to make braille cells, for instance, with this technology. This is also useful for object manipulation, as you just saw. And this also has some interesting applications for robotics, which I'll touch on kind of later in this talk. But I actually want to zoom out a little bit further because what really motivates me to work in this area is not just these shape-changing objects, but really the concept of shape-changing environments. So to give you an example, let's take a look at my apartment. So my apartment is small, but what's cool about it is that I have these really unique walls. So when I come home from the grocery store and I'm got my hands full of the grocery bag, my wall helpfully turns into a little shelf for me. Now that my hands are free, I can take off my jacket, and well, this coat hook just appeared up on top, so I can hang my coat up on the coat hook over there. And then when that's done, I can grab my grocery bag. My helpful wall will just kind of raise my jacket out of the way. And the shelf, since I don't need it anymore, can just collapse right back into the wall and can free up a lot of space in my very, very tiny apartment. So this is an example of a robotic surface that's been embedded into the built environment, right? It's a robotic surface at architectural scales. And this opens up a kind of a space of interactions that I feel are almost kind of magical, right? If you've seen the Disney movie Encanto, for example, the whole house is alive, right? Tiles on the wall can flip out and move objects around. Floorboards can shuffle and interact with characters in the film. It's a tangible interface and a robotic companion kind of all in one. So given that these robotic surfaces are interesting and useful, which I hope you agree that they are, where are they? Why are they not here in this room right now? Why is it that that wall over there can't turn into additional seating or a breakfast bar or a little alcove or nook? And one of the simplest reasons is that they're still just really hard to make, right? So to get a sense of why this is, let's make this more concrete and look at the bubble surface again from the beginning. This is the same surface that was steering that ball around. Let's say you wanted to make something like this, where you could control each of these individual bubbles, make them inflate or deflate. How would you go about doing it? Well, one way you might build it is to attach, say, a solenoid valve to each of those little transducers to regulate the airflow into those bubbles. So you buy it from some supplier, you attach it over there, and then you do it to the next one, and then you do it again, and then you do it one more time, and then you just do it a couple more times, and then you can see that very quickly this becomes a really labor-intensive process, right? Because each of these actuators are discrete mechanisms, and so you have all these repeated assembly steps for each of the actuators in your system. And so that's part of the reason why in the literature these programmable surfaces have been kind of constrained in size, right? On the top right here you have an example of a pneumatic surface with solenoid valves. On the bottom you have an example of a lead screw-driven surface. There's different mechanisms, but it's the same module-driven approach, right? There's lots of independent pieces here. So how can we avoid all this assembly? Because if we make these surfaces easier to manufacture, then maybe we can get to the point where they're embedded into these environments. And so one idea is that instead of putting together a bunch of separate actuators, we could instead think about these surfaces in terms of patterned layers. So the idea is that we can use these very mature fabrication techniques like photo etching or laser cutting, et cetera, to make these layers all at once. And then the assembly process is just stacking them on top of each other. So whether we have 10 actuators or 100 actuators, the assembly process is still the same. So on the left side, we have a module-driven design with solenoid valves. And on the right side, we have the kind of layer-driven equivalent. This is an array of electrostatic valves. So now, if you spend a lot of time looking at PCB stack-ups, you might be glancing at that image on the right and getting a couple ideas here. And we had the same idea. So together with my collaborator, Scott Hudson at Carnegie Mellon, we decided to kind of hijack the layup process for printed circuit boards and insert these patterned electrostatic valve structures inside PCBs. And so this is what I'm going to talk about right now. So here's an example of one of our pneumatic surfaces. We're rendering a couple different patterns an arrow left, arrow right, deflating these bubbles. If I take off the lid of this little surface, you'll see that we've got this passive transducer on top. This is just a piece of cast silicone. And it's sitting on top of this printed circuit board that looks like this. This is our control layer, but what's kind of neat about this is that the valves are, in a sense, like baked into this printed circuit board. So you see on the backside, we've patterned some copper electrodes, and when we combine this with a conductive diaphragm, this forms the basis of our valve structure. And what's really great about this, or what's great about having valves kind of patterned on a PCB, is that the assembly process, as I said, for one actuator is the same as the assembly process for 7 or for 127, right? So let's get into how this works. I'm going to go to an exploded view of our electrostatic valve structure. So again, we have this kind of bubble transducer on top, but this transducer can really be anything, and I'll show some other examples of things you can stick on here in a moment. In the non-active state, these bubbles are raised. They're actually bistable, so when you kind of suck air out of them, they kind of snap down through, kind of like those fidget toys if you've ever played with those, or those kind of pop-up little toys. So again, we suck air out of these bubbles into this kind of global pneumatic sink we have at the bottom of our structure. Air travels from the bubbles down through the valve inlets, through the valve outlets, and then into that global pneumatic sink. That's where we've attached our vacuum. And that deflates a bubble, or collapses a bubble. So let's say we want to keep the bubble intact. How do we do that? Well, that's where our flexible diaphragm comes into play. This is going to regulate the air that flows through the material. And the way it does that, I'll show you this kind of cross-section over here, is using electrostatics. So you see on the right side a cross-section of the structure. Let's talk about kind of the kind of default non-active state first. So we've got these valve inlets on top. We've got the valve outlet on the bottom. In red, we have our flexible conductive diaphragm. And in yellow, we have this copper electrode that the diaphragm sits directly underneath. And it's separated by a layer of solder mask, actually just 15 microns thick. So in the non-active state, when there is no airflow, the voltage is off, what happens is, let's say we apply a vacuum to this system. So we've got high air pressure on top, we've got low air pressure on the bottom. What happens naturally is that that mylar valve, or sorry, that mylar diaphragm, I should say, gets pulled down flat against the valve outlet. And that stops airflow. So this acts kind of like a check valve if you've worked with those before. So no air can flow here. Now if we want to activate this valve and let air flow through this structure, what we can do is apply a voltage across that top electrode and the conductive diaphragm. And so as a result, one of these is going to be positively charged, the other is going to be negatively charged. That diaphragm is going to cling to that top electrode, and that's going to let air pass through the cell, right? So here you can see, I've taken off one of the layers. You can see I'm just kind of toggling the voltage right here on and off, and you can see how that mylar diaphragm clings to that top electrode. And now there would be another layer on top of this, but if I had it on there, you wouldn't be able to see, that structure there. Okay. So you might have noticed that there's kind of this bonus electrode also at the valve outlet. You can see that on the left side of the diagram as well. The reason for this is that sometimes when we are applying a vacuum, normally everything works fine and the valve diaphragm, gets pulled down to the outlet, but every so often there's a little bit of leakage which we don't want, and in those situations what we do is we just apply a voltage between that sealing electrode on the bottom, which we call it, and that mylar diaphragm. And that seals everything up nicely. No air gets through here. Cool. Now, since this is the Hackaday audience, I wanted to talk a little bit about the process of getting here, because we're actually doing something that's a little bit unconventional with the valve structure. So initially our idea was to use these mylar diaphragms as lids. And the idea, here you can see I've got like a very early kind of prototype valve, and I'm trying to use this mylar lid essentially to block airflow. And I'm pumping using a syringe to kind of pump air into this structure. And you can see it's not really working very well. Every time I try to pump air in, that little mylar flap is not doing a very good job of blocking air that's kind of going through there. But what I did notice when I was doing these early experiments is that when I wanted to kind of reset this setup, when I wanted to pull the syringe back so I could kind of do the process again, it was actually really difficult, because a lot of the times that mylar flap would get stuck down and plug the whole system, and I wouldn't be able to move that plunger at all. So I said, okay, let's take this problem and actually use it to our advantage. So let's take this lid structure and just turn the whole thing upside down, and that should be our valve. And that actually worked pretty well. This was our first little breakthrough, essentially. So here I'm using that kind of back syringe to control that front one. When the voltage is off, I'm not able to move this at all. I'm yanking on that syringe, nothing's coming through. When I turn the voltage on, now I can move that front syringe using that back syringe. So I was very happy about this. After this, I made a whole bunch of different prototypes, way more than I'm showing here, to kind of get the diaphragm geometry right and the spacer materials correct. And eventually we came to the structure that I was just telling you about before. And there's still optimizations to be made here, but overall these valves are not too bad. They open fairly reliably in about 40 milliseconds or so. And generally they operate at around 300 volts. But if you're clever about the actuation scheme, you can actually get them to operate around 200 or even less. And so what I mean by that is that if instead of having just a vacuum at kind of the bottom of this structure, if we instead have this kind of alternating pressure source, we could take advantage of how the diaphragm moves up and down to drive this at a much lower voltage. I'll show you an example. So let's say we kind of start in a situation like this, and let's say we want to collapse that left bubble over there. So we have this alternating pressure source on the bottom. We're pumping air in. The diaphragms are moving up to the top of the cell. And because the distance between that diaphragm and the top electrode is now collapsed, we can sort of catch it here at a much lower voltage than we normally would be able to, right? So we latch it in place, essentially. Then when we suck everything back down on like the downstroke of our alternating pressure cycle, that's when we can deflate that bubble over to the left. We can repeat the same process, right? Pushing up, latching, this time on the right, pulling down. So here's the whole sequence, in case you're interested. Now, this particular actuation style will limit you for certain applications, but if you throw the right transducers on top, it can actually enable a lot of really cool things. So all the stuff I kind of teased at the beginning of this presentation, the braille cells, the bellows, this little rimless wheel, this is all done with that same actuation scheme. What's kind of fun about this one is we basically have this 3D printed piping structure that we've attached to a grid of valves which is on its side. So all the valves that control each of these syringes are actually inside this very thin little hub. And this where I can kind of walk around a table or do some fun things. Okay, so if you're interested in how these valves talk to each other, or this kind of stacked manifold which we can use to kind of flow air around, you can talk to me after this talk, because right now what I really want to talk about is the fact that these structures are mostly flat, right, or kind of 2.5D at least, right? All the deflection is normal to like this kind of base surface. So, what I want to know next is kind of, okay, how do we leave the plane? And you may have noticed that the title of this talk is not just circuit boards that breathe, but it's also circuit boards that breathe and bend. So at the time I have left, I want to talk a little bit about bending, or more specifically, I want to talk about folding, actually. So let's start with a flat robotic structure. So here we have blue pieces that represent rigid members, and these yellow pieces are hinges that we might want to constrain in a rigid orientation, or a mountain orientation, or a valley orientation. And we borrow these orientations or this terminology from origami. And so the thought was, okay, we can start flat, we can manufacture all these things as flat sheets, but then we can add these low power constraints, and when we squeeze this whole surface together at the sides, we can kind of pop out of the plane and enter a whole new shape space. So together with, again, Dr. Scott Hudson and Dr. Alexandra Ion, we set out to explore these constraint-driven robotic surfaces. And from the very beginning, we knew we were interested in working at architectural scale. We thought, oh, how neat would it be if you could just have this big, wall over here, and you could summon a shelf over here, and you could, then summon a shelf over there, and the whole thing could collapse back in. So here we kind of put the pneumatic structures aside just for a moment so we could focus really on this folding mechanic and kind of nail that. So here's our surface again. This is the one I showed at the beginning. You can see a shape popping out of the wall here. And you'll notice that there are motors at each of these joints, but they're very small. And that's because these motors are not actually bending these kind of cells relative to each other. They're actually just constraining the cells in these rigid orientations, these mountain orientations, and valley orientations. They're just toggles. They're not actually kind of doing a lot of actuation here. And the way that the surface is formed is by squeezing the thing from the edges. All right, so, yep, you can see that over here. So we can constrain these, or change these constraints rather, programmatically. for every single joint of the surface here. So for example, we could construct a completely different shape. We could say we want to start with a rigid beam over here. We want to change the appropriate constraints, add mountains and valleys. And then we can squeeze from the edges to get a new shape to kind of pop out of our robotic wall structure. What's cool about this is all the powerful actuation, again, is coming really from the edges here. And internally, we're just using more or less the cheapest actuators we can get. This is actually, the retraction mechanism is really fun too, because it's just us shimmying the endpoints back and forth, so it's a really kind of cool control problem to get this to kind of collapse back in here. So let's take a closer look at the constraining mechanism. So here you can see one of our columns. The top and bottom kind of panels here are, you can think of them as rigid flex PCBs because they essentially are rigid flex PCBs. So we've got these hinges that are integrated into the structure itself. And at each cell, we have this 3D printed kind of semicircular clamp, which can rotate to constrain hinges in kind of the top position or the bottom position, or both. So you can see here, we start as a rigid beam. Excuse me. And then when we rotate, select constraints over here, we can sort of program this column to form the appropriate mountain and valley constraints. And then we squeeze to get our interesting shapes. And you'll notice here also that there's wires here that connect these small motors to the PCBs at the bottom, but there's not additional wires that connect one segment to the next. And so that's because power and signal is actually all running through the structure itself. So these are our hinges before we make them into boxes. We manufacture these, again, as flat sheets. So this is a sandwich of FR4, Mylar, and a heat-activated adhesive for these kind of flexible hinges. We also throw in these flat flexible cables as kind of a cheap DIY alternative to a more proper rigid flex circuit structure. And so we take all these layers, we sandwich them together on the heat press. On the left side, you can see that's our Mylar and adhesive, which we've kind of pre-laminated, and in this case, kind of pre-cut. We lay them all up there, squish them all together, and then we kind of cut our sheets into these strips. We add these jumper boards, which mate with those internal flex cables. This is how we join one cell to another, but this is also how we join one strip to another. So this is how we get to these like 2-meter-long columns from that initial, 15-inch, square inch or so, or square on each side, panel. We then add these 3D printed side frames. Now, ultimately, what we like to do is actually have this whole structure be assembled from a flat sheet, right? You can imagine like an origami box that sort of folds up. But for kind of ease of prototyping, at the moment, we're just using these kind of 3D printed pieces. And this is what we end up with. So you can see we've got our kind of constraint driving motors internally, or constraint toggling motors, you could also call them. Each column is controlled by a PCB that rides on the bottom endpoint of the column. Both the top and the bottom endpoints are movable. They move on these rails. And we have a belt drive system that moves both of those. And there's a worm gear on that drive, which is really nice because once we've kind of moved everything into the right position, then it doesn't require any power to stay in that shape, which is super helpful if you're trying to do reconfigurable furniture and things. So we can do a lot of fun stuff with this. Here, my wall is telling me that it's raining outside, so I need to make sure I take my umbrella with me. It's very important. All right, thank you, wall. I'm going to take the umbrella. Okay, very nice. We can also explore reconfigurable architecture. Here we've constructed a little reading nook that somebody could sit underneath. They have a nice little canopy. We're raising this again kind of from the bottom end point this time, and the wall is also angling a little light for us. And here I'm using a wall as the temporary laptop stand. So I've kind of walked up to this, and I've placed my laptop here to do some work, and I decide to kind of adjust the height, and the wall raises up, and I can work at this kind of different height over here. So the commands I'm typing in right now, I've SSH'd into the wall, which is kind of a funny concept. Yeah. And again, it collapses back when we're done. All right, so where do we go from here? So a lot of the demos I've showed you just now are relatively pre-scripted, right? What I'd like to kind of go next with this is really kind of embed some sensing inside of here for some really rich physical interactions. You can imagine, since we're already using printed circuit boards, it's not too crazy to imagine capacitive sensors embedded inside of each of these that enable touch and other kind of interaction modalities. Another thing to consider is that with this wall in particular, we've kind of brought back some of the assembly steps by adding in these individual motors here. So as kind of a next step, can we marry this structure with our very thin, very easy to manufacture valve structure and kind of perhaps toggle the constraints this way pneumatically to really make this kind of structure truly scalable? And for the valves themselves, are there ways that we can kind of make these thinner? Can we add some flexibility to them? Can we embed them perhaps in soft robotic surfaces or plush toys or clothing? If any of that sounds interesting to you, I invite you to please stay in touch. I've historically been very bad at doing anything that's social media related, but I'm trying to share more of my process now, so you can join a very exclusive following of, yeah. Or you can check me out on Instagram if you prefer. My handle is jesse.t.gonzalez on both of them. Thanks.